Hello everyone, what we're going to do here is find the length of the curve. This is a multivariable calculus topic. The curve is given by this vector function here. Let's talk about a bit how to sketch that curve. So what we're going to have is a curve here, and I'm going to start off by, well, first of all, I'm going to start maybe by writing this vector function in component form, because I think I like it that way sometimes. That's component form. Another form is to express parametric equations for the curve, which just means I'm going to take out the x, y, and z coordinate functions. And I am going to try to give some idea of what the curve looks like, beginning with looking at z, which is z is e to the negative t, which is the same thing as 1 over e to the t. However, e to the t is y, so this gives 1 over y. Also, when I write z equals 1 over y, let's keep in mind that because y equals this exponential function, that y is greater than 0. Y is greater than 0. So let's just sketch this z equals 1 over y in the x, y, z space. So, okay, I have this over here, and okay, this is the x, y, and z axis. Z equals 1 over y can be thought of as a curve in the yz plane, and I will now sketch that curve. So this is sort of one of the ones that maybe people memorized. Z equals 1 over y, but in general, z equals 1 over y is also down here also. But since y is greater than 0, we just have this part here. Now this is in the yz plane, which corresponds to x equals 0. But see, there's no x here, so x could be 0, x could be 1, in which case a copy of this curve is, it could be right here. And infinite copies in between. Except that's going to sort of ruin my picture a little bit, but that's what we have here. And so this is actually a cylinder. It's not a cylinder like a soup can. It's the definition of a cylinder in three-dimensional space, where you have a curve in the y-z plane, and then you have an infinite number of lines orthogonal to that curve that form parallel lines orthogonal to that curve that form a surface. All right, that was sort of a bit of review of how to sketch a surface right there. So that's the surface z equals 1 over y. It looks like a sort of a cool modern chair to sit in, maybe, perhaps one would say. Sort of habit of mine, but maybe other people have thinking what that cool figure looks like, or surface looks like. So a little bit of a problem with what I do is I start getting too much into the drawings here. So you have that surface, and the curve that we're looking at lies on the surface. So the curve lies on the surface, and to see what curve that will be, let's check out this part over here, this with x and y. So if x equals rad 2t, then we can easily see that t equals 1 over rad 2 x. But going from over here, y equals e to the t, and t is 1 over rad 2x. So what we get is an exponential function, and we know that graph. And then also, let's just point out what r of 0 is. That's going to be square root of 2 times 0, e to the 0, e to the negative 0. So this is 0, 1, 1. Okay. So this is, all right, let me go ahead and sketch this curve projected on the xy plane, because I have this function here in terms of xy. So this is just a exponential curve. Well, let's multiply by a constant, 1 over rad 2, but it doesn't really change that picture very much. And so that's what it looks like on the xy plane. And so the r curve is just the same, it's a curve that's sitting above this on the surface z equals 1 over y, or y is positive. Now this is only a piece of this. This is only one piece of this, and so the surface is infinitely large and the curve goes on infinitely. Let's just check out what r of 1 is. It doesn't really help us that much, but still. This is rad 2 times 1, e to the 1, e to the negative 1. So, we get a couple points there, and we can get an idea of what this curve looks like. And I did it in, for some reason I just thought, oh, I like the color brown, but it doesn't really pop out. I don't know what. Anyway, that's C. Okay, so I have that, and that was absolutely not necessary to do this problem. So that's sort of a lot of stuff that wasn't even part of the problem. Now we're going to do down the arc length. We're going to find the arc length. That's the problem. The arc length is given by L equals the integral from A to B, magnitude r prime of t dt. So now we're actually going to solve this problem. In our situation, A is equal to 0 and B is equal to 1. And let's actually have to find out what r prime is, but r of t is rad 2 times t, e to the t, e to the negative t. That was given to us. And then r prime, I do this derivative, not the hardest thing here. Square root of t is 1, so square root of derivative of t is 1. Derivative of t is 1, so I get square root of 2. And then e to the t, I get derivative of e to t. E to the negative t, that derivative is negative e to the negative t. Magnitude of that is square root of square root of 2 squared plus e to the t squared plus negative e to the negative t squared. All right. Now, the thing about this is it might not be so clear, but this simplifies quite a bit. Here we have the negative squared. Negative squared makes positive. So, okay. So let's see. Plus e to the negative 2t. All right. This actually simplifies into what? The square root, these part under the radical, I guess called the radicand, simplifies to e to the t plus e to the negative t quantity squared. Huh, really? Can we see that? Well, you can expand this to see that's true. I mean, part of what you would see is that you have 3 terms. And 2 of those terms are square, perfect square. It's a square, e to the t squared, e to the negative e to the negative t squared. So you have 3 terms, a trinomial. 2 of them are squares. So you think it might be in this. And so what you can do is just check. E to the t plus e to the negative t squared. It's the first term squared plus 2 times the product of the terms plus the second term squared. And so the thing is why this is sort of tricky is this sort of cool thing that we have e to the t times e to the negative t makes 1. Because see, you add the exponents, t plus negative t, so that makes 2 e to the 0. So that makes e to the 2t plus 2 plus e to the negative 2t. So that's something right there. And so then this gives us, all right. So then I have the square root of something squared, which gives the absolute value of e to the t plus e to the negative t. In general, square root of a quantity squared, that gives the absolute value of that quantity. However, expression. However, since e to the t and e to the negative t are positive, we don't need absolute value there. Now we're all good to go. Now the thing is that these problems, when these arc lengths are not in general very practical to find the answer, to integrate. So this is a homework problem where there's some little trick that was very cool. But if we tried to integrate, say, this right here without seeing this simplification trick, it really wouldn't work out easily at all. It would be it could be very difficult, I guess. It has to be some little trick, which there was here. Okay, so we do the antiderivative. Antiderivative e to t is e to t of e to the negative t is negative e to negative t. That might throw you for a, stop you right there. In general, the side here, the antiderivative e to the kt is equal to 1 over k e to the kt plus c. How do you know that? Well, you can use u substitution. I mean, let's think about it, though. The derivative e to the kt is k times e to the kt. So you think this antiderivative is going to be e to the kt times a constant, and you just play around with it. E to the kt, take the derivative, you get k e to the kt. So k times 1 over k makes 1. So in this case, k is negative 1, so this minus is actually 1 over negative 1. And then we can go ahead and plug in e to the 1 minus e to the negative 1 minus e to the 0 minus e to the negative 0. So this gives e minus 1 over e minus 1 minus 1. So that gives e minus 1 over e. So we sketched the graph, which was not asked, which was beyond what was asked for. And we found so we sketched the graph of the curve, and we found the length of the curve. In my graph, it sort of has an appearance as if this point here is on the xy plane. That's the sort of the issues of drawing, a three-dimensional figure. It could be hard to get everything right there in the drawing, but it's supposed to be lying above there. And okay, so let me zoom out, because I did sort of flip quickly there. Okay, so let me zoom out, and that is the whole problem. Take a screenshot or something. Okay, thank you, bye.